So this is lesson 4.5 in your unit handout, called Properties of and Types of Waves. And there's a lot of qualitative work that we need to cover today. There are some calculations we will get to. This is a very important aspect to physics because in Physics 30, 1/4 of the course, actually a little bit more than 1/4 of the course, deals with what's called electromagnetic waves, which are a type of wave motion. And almost everything we study from here on in this unit continues on some level in Physics 30. So we're dealing here with the difference between what's called a mechanical wave today and an electromagnetic wave. We're going to be looking at the difference between longitudinal waves and transverse waves, and we will get into the nuts and bolts of this in a few minutes, but mechanical waves are a certain type of wave that are sometimes longitudinal and sometimes transverse. Okay? It isn't that there's 4 types of waves. It's not that there are mechanical waves and electromagnetic waves and transverse waves and longitudinal waves. There's 2 main types of waves, mechanical and electromagnetic. And mechanical waves, it turns out, can be longitudinal or transverse. It turns out electromagnetic waves are transverse, period. The unit in Physics 30 that we study in detail dealing with waves is called electromagnetic waves or electromagnetic radiation. As well as knowing the difference between longitudinal and transverse waves, we need to understand the properties of those waves. And then we're going to be solving some problems involving period, frequency, and speed of a wave. The period of a wave is going to be the time it takes the wave to do its thing once. The frequency of a wave is going to be how many times per second the wave does its thing, whatever its thing is. And the speed is how fast the energy moves through the wave. So to begin with, how is it that you can transfer energy from place to place? And the answer to this question is fundamental in this course and Physics 30. It turns out there's only 2 ways I can transfer energy from one location to another. It can be done by particles. And when I say particles, we use the word particles in physics, but particles could be, a deck of cards or a 3-hole punch or a piece of cherry pie. Could be anything, something with mass. And if I want to transfer energy to you using a piece of cherry pie, particles, I could throw the piece of pie at you, and when it hits you, it transfers energy to you. Sorry, I didn't mean to startle anyone. Okay? So that's one way that it can be done. So what we're talking about here is simply motion of an object from one place in space to a different place in space. On the other hand, we can use wave motion, which does not involve the motion of matter from one place to another. It doesn't. So here, under particles, we can write a physical object, or an object with mass, carries the energy. I'm not going to write this, but from one point in space to another point in space. That's what we're talking about when we talk about transmitting energy from a location to another. It's more difficult to write out what we mean by wave transmission of energy. So maybe before we do that, we can come up with a couple of illustrations of what I'm talking about. Some very simple examples. If I were to take a piece of rope, and you held one end of the rope and I held the other and we pulled it tight, and I do this to the end of the rope, I give it a quick shake, you're going to feel something on the other end, right? So that's because there is a movement of some substance. In this case, it's the rope. But the energy moves through the rope. It's very similar to the fact that sound is a wave. We'll learn more details about sound waves a lot in this unit. Sound is a wave, and it's transmitted by air vibrating and bouncing around. But when I stand over here and I speak to the back of the room, the air doesn't pile up at the back of the room. The air does some kind of motion, and the energy as a result of that motion goes through it. The classic example that I've used before, and I don't know if I've used it here, is imagine that we have a room that's filled with Jell-O. I've talked about that. And there's a sheet of plywood resting on the Jell-O on one side, and there's a sheet of plywood resting on the Jell-O on the other side, and we, through a series of ropes and pulleys and tackles, we lower ourselves down there. And if I start kind of bobbing up and down on my sheet of plywood, you're going to bob up and down on your sheet of plywood a short time later. But that's not because I threw a bucket of Jell-O at you. The Jell-O has something to do with how the energy is transmitted, but the energy itself is not the Jell-O. It's not the motion of the Jell-O. So the best thing I can give you for a definition of a wave right now is a vibration of a material that results in motion of energy. Or I'm not going to use the word motion or movement. That's a bad move, no pun intended on my part. I'm going to say transmission of energy. So it can be a transmission of energy through vibration of Jell-O. It can be a transmission of energy through vibration of air molecules. It can be a transmission of energy through a vibration of anything. The floor. An earthquake, it turns out those are waves. It's the earth oscillating up and down in places, and the energy, even though the oscillation and the disruption to the earth's crust might happen in northern Italy, in Greece, you feel it. And obviously the landmass that is called Italy is not moving closer to Greece when that happens. Okay, there is some shift of the Earth's crust, but that's not what's causing the energy to vibrate or to transmit. So now we're going to go through some definitions today. Officially, a wave is a disturbance, and that disturbance could be a vibration, an oscillation, a bounciness, a back and forth motion, any type of motion you can think of a medium, so of a substance that carries energy from one point to another without actually moving the material. I mean, that's a pretty wordy definition. It's more of an explanation than a definition. The medium of a wave is simply the material that is doing the vibrating. So when we talk about a sound wave, the material or the medium of a sound wave is air. When we talk about a water wave, the medium is water. When we talk about a Jell-O wave, it's Jell-O. When we talk about a wave on a spring or a rope, it's the spring or the rope. Now, types of waves. There are two types of waves in general, and the type of wave that we're going to be studying in detail in this unit are mechanical. This course is called, the unit is called mechanical waves, not electromagnetic waves. But we can classify waves as being mechanical or electromagnetic, and what a mechanical wave is a wave that has a physical substance. And I know this is going to seem weird to you because I'm telling you by saying that there are some waves that do not have a physical substance. They do not have something physically that's vibrating. They have something else that's vibrating. But the thing that's vibrating in an electromagnetic wave isn't something physical. It's not substance. So two examples of mechanical waves that you should be very familiar with are sound waves and water waves. If I am sitting on my floating mattress someplace on vacation, sipping my pina colada, listening to my music, and a boat goes by, maybe 100 meters away, a big boat leaving a huge wake of water, after a short period of time, my mattress and I will start bobbing up and down. I will be given energy. But again, it's not because the water hit me directly. That's evidence of a wave. A sound wave, it's the same type of thing. When I'm speaking, actually, my vocal cords are causing the air to vibrate in a certain pattern, and that pattern, like a domino effect almost, is reproduced, and it keeps repeating over and over and over again away from me, and eventually it hits your eardrum and causes your eardrum to bounce around in the same way that my vocal cords are, and your brain interprets that as sound. But it's a wave. Electromagnetic waves have no actual physical medium that vibrates. This is a mystery that physicists in, say, 1900, 1905 really had trouble with, because light is a wave. Okay? It turns out light is a wave, and you can do things with light called interference and diffraction, and when you see light interfere and diffract, which we will learn about, you go, there you go, light's a wave, because only waves interfere and diffract. It's irrefutable, which means you can't argue it. Radio waves, radar, gamma radiation, X-rays, microwaves, ultraviolet, infrared, all of microwave, if I didn't mention it, all of these are types of waves, but there's no physical substance to them. And in 1905, roughly, they did a whole bunch of experiments to try to detect if there was a physical substance for light. And it turns out there isn't. So try to wrap your head around that. Light is a wave of something oscillating, transmitting energy, but the thing that's oscillating has no substance to it. There's nothing there. I can tell you right now what's oscillating are fields, an electric field and a magnetic field. It's complicated, and that's why it's saved, I guess, for Physics 30. Incidentally, just so you know, you're familiar with the concept of the speed of light. You can look it up on your formula sheet. That's the speed of radio waves. That's the speed of microwaves. That's the speed of radar. That's the speed of any type of electromagnetic wave. They all travel at the speed of light. All right, now we're going to focus mainly on mechanical waves for the rest of the lesson and unit. Waves can either be transverse or longitudinal. And what determines whether a wave is transverse or longitudinal is how the medium is vibrating compared to how the energy is moving. Okay, and there's a difference. So, and I'm going to show this to you with a number of demonstrations and illustrations. If the vibration is perpendicular to the motion of the energy, that's transverse. And some people have a difficult time remembering that, but if you look at the perpendicular symbol, it looks like that. Which is an upside down T. T for transverse, flip it over, it's perpendicular. Okay? What do I mean by that? I mean that visually, the medium is mostly bouncing up and down. We very rarely have a transverse wave that doesn't travel horizontally. A water wave is a transverse wave. The medium is oscillating up and down, and the energy moves, say, left to right. So the angle between those two directions is 90 degrees, which means it's perpendicular. So this is an example of a transverse wave. And if those white dots were not on there, you probably wouldn't realize that something is moving up and down, right? What you would probably just see is the peak or the crest of that wave moving to the right. In fact, even right now, it's hard not to just focus your attention on that. But if you take a look at any individual point, every point is moving up and down. I can make that a little easier to follow by going to not as rapid of an oscillation, to what we call a lower frequency. So every single point, and you can see this one that the rectangle is around, every single point is simply moving up and down. Every single point is a simple harmonic oscillator. The only difference is each point is connected physically to the next point, and it's in oscillation slightly out of delay. And there's a reason for that. This is a really silly analogy. Really silly analogy. But if I take, I won't use high school students, I'll take grade 1 kids. Okay? And I line them up and I tell them to hold hands. and I say, don't let go. Hang on. And I grab the free hand of the person on this end, and I start swinging them back and forth like this. Do you agree that down the line, this person at the other end is going to end up going back and forth? But there's a time delay there, right? The second person moves back and forth because they're connected to the first person. But things take time to happen. I don't shake the first person back and forth and the whole line goes back and forth. It's just the first person. And as the first person comes towards you, then they drag the second person towards you. And the first person is already on their way back, and the second person is still moving towards you. So this is kind of a way to visualize what's happening here. The reason why they're all dancing to the same beat, but slightly out of tune with each other, is it takes time for that action to transmit through the medium. So this is an example of a transverse wave. Here's another illustration. I don't know that it helps to see a variety of these, but we can take a look at a couple. I mean, right there, it's very difficult for you. If those points were not colored, I think you would be hard-pressed to understand what's physically happening here. And maybe prior to today, you didn't even realize that that's what a wave is stuff moving up and down, or a water wave anyway. I can make this a little easier to follow by doing that. And we'll talk about what wavelength is and all of those things in a bit. But that's what wave motion is. And these are examples of transverse. Going back to your lesson, this is a nice graphic. I can't find it online anymore, so I clipped it a number of years ago. It is a very nice graphic because there's so many particles in there that are bouncing up and down. It's hard for you to understand that things are not physically moving to the right. Energy is, which is why if you're on a surfboard and you angle your surfboard on the top of one of these crests, it's going to push you. It isn't that the water is moving with you. The energy is pushing you. So that's a transverse wave. A longitudinal wave is one in which the vibration is parallel in the same direction as the energy transmission. So what this looks like pictorially is you have something that vibrates back and forth, and the energy moves in the same direction as the vibration, say to the right. I think what I'm about to show you is one of the most amazing illustrations of a longitudinal wave, because nothing, even though it looks like something is moving to the right there, if you follow any of those dots, they stop and move back and forth. And they're not even doing it very rapidly, are they? They're just drifting back and forth in a certain way so that you see that energy moving through it. Now, I will show you a physical example of a transverse wave in a bit. This is a longitudinal wave. This is a really good demonstration of the energy moving through a longitudinal wave. And what's basically happening here is the kids are all next to each other, shoulder to shoulder, but I'm not swinging them back and forth. I shove the first kid. And they hit the second kid and bounce back, and the second kid hits the third kid and bounces back. But the result is you get these, we call them compressions of energy moving through. And if I take this and I pull it back and let it go, it's going to cause that compression, and it's very clear that it moves through. You get a series of those compressions. Now the wave then hits the end and it reflects back. Okay, if it reflects back, you get other things happening like interference. And I'll do this once just by moving this back and forth once rather than a repetitive thing. And you can see the energy go through. And if you didn't know what was going on, you know, take one of these grade 1 kids and ask them what's going on, they would probably say that the spring is moving to the right. But it's not. The spring is just being compressed and pulled apart in different places. So that's an example of a longitudinal wave. I can show you a couple of online We'll go with this one first. It's really hard for you not to believe that there's something piling up and moving to the right. But if you look at any individual point, and it's very difficult to see here, so I'll change the frequency. If you look at any individual line there, every line is simply moving back and forth. We'll take a look at this one too. This is a really good one. Because it contains more than one of those compressed regions of the medium. It also has a couple of lines that are highlighted. One is green, and you can see it moving back and forth. And these lines are not even moving back and forth that fast. They're moving back and forth with a slightly different frequency now, and the wave is moving faster. So, longitudinal, the direction of vibration is parallel to the direction of motion. Most people do not have any difficulty remembering this, but if you write the word L, if you write the letter L for longitudinal, it contains two lines that are oriented in the same direction. One way or another, you're expected to know that longitudinal waves are this type of motion, vibrating back and forth, and the energy traveling in one of the directions, either back or forth. And transverse is this type of wave motion. Any questions between those two types of motion? Okay, let's take a little field trip out into the hallway. And you know, those demonstrations aren't much, really. I mean, in comparison to this is showing you an awful lot more about what's going on with a longitudinal wave. And with a transverse wave, something like this is certainly showing you what's going on in a cleaner, more perfect fashion. But I still think it's kind of interesting, cool, whatever word you want to use, to see that in action on an actual piece of material. It's the same with this one, right? This idea that, and I never asked, but everybody on the far side of the room, could you see that okay, this? I mean, I just have to move this, I'll move this up here. I just have to move this back and forth once. Or just do that. And it sets that kind of accordion effect into action. So that's what a sound wave is. When I'm speaking, this is really kind of cool how sound works and hearing works. We've evolved so that I can make certain noises by moving the air around. And we've created language out of that, you know, somewhere along the way. And we've evolved as well as being able to make these movements of air. We've evolved so that our ears can pick them up. I'm like a radio transmitter, and your ear is like the antenna, except that would be an electromagnetic wave. This is a mechanical wave. Those air molecules in front of my mouth bounce back and forth with the pattern that I'm creating, which is called sound, and that pattern is repeated until it hits your eardrum, and then when your eardrum does that, your brain hears the sound. Any questions about longitudinal or transverse waves? All right, and thank you for your help out there. So some other definitions. The equilibrium position of either of the above types of waves is the position or state of the medium if no disturbance is present. This should be no surprise. So if I were to take a look at, I don't know if I can get these here. Yeah, I can. If I were to take a look at this state of affairs, that's the equilibrium position of a transverse wave. If I were to take a look at if I were to take a look at that state of affairs, that happens to be the equilibrium position of a longitudinal wave. So if there's no talking or noise in the room, the air is all evenly distributed. Okay? And if there's no water wave, then the water is nice and flat. That's what the equilibrium position is. Now, the following terms are only applicable to longitudinal waves, which is this type of wave. Now, do you see when I did that, I did kind of get this kind of motion as well? That's not what we're talking about. We're talking solely about that. And I want you, before I show this to you, to just take a mental snapshot of one of these images. There are places where the spring is pressed together. But the overall length of this spring or slinky or whatever you want to call it is not shorter because those pieces are squished together. Which means there are also pieces where it must be stretched apart. If I go to my analogy of those grade 1 kids, and it's not a perfect analogy obviously, but I shove that first one towards the end of the other end of the line, at some point their shoulders are going to be squished more together. But that means there are going to be some students who are further away from each other to compensate for that change in density. A compression is a region of high density. The compression is what you probably see or focus on when you look at this. You're focusing on this thing, and that's the compression. What you're not focusing on is the fact that these lines, halfway between the two compressions, are stretched further apart. If you take a look at this distance here, between those lines, and you look at the average distance between the lines, the distance between the lines in the middle here is greater, and the distance between the lines at the compression is less. So we say that a compression is a region of high density, and I don't know who came up with this word. I don't dislike many words, but I don't like this word. Rarefaction or rarefaction. It doesn't roll off the tongue like most language does. It's a really awkward word. And consider as well that later on we will learn about something called refraction, which is different. Okay? So a rarefaction is a region of low density in a wave. The wavelength, and you have all heard about wavelengths, haven't you? Maybe not in a scientific way, but you might have encountered the word in other places. The wavelength is the distance between two successive compressions. It's the same as the distance between two successive rarefactions. Assuming that the wave is a regular wave, in other words, somebody is moving one end of the medium back and forth at a regular rate and they're not changing it. They're just doing the same thing all the time. Then the wavelength is the same as the distance between the rarefactions. The symbol for wavelength is lambda. It's a Greek letter. It looks like kind of an upside down and reflected Y. I don't have the time or the inclination in my life to draw it with all the details, the curvy details. I just draw it that way. On this diagram, and this is just a snapshot, by the way, of this. I've changed the scale and stuff. On that diagram, we are asked to label a few things. We want to label any compressions, rarefactions, and the wavelength. Well, this is clearly a compression. So is this. You can label them however you want. And I would just say to you in general that this is a rarefaction. You know, are there rarefactions over here on the left and the right of the diagram? Probably, but we're not really right at the rarefaction there. It's a little bit further off to the right or a little bit further off to the left. What is the wavelength? The wavelength is the distance between here and here. This is the wavelength. That's lambda. Had I been thinking a little more clearly, I would have written that other compression on the bottom so that I could draw those arrows above a little bit more. But I think you get the idea. That's the wavelength. The following terms now are related to transverse waves. So equilibrium position was a general statement that the equilibrium position of a wave is what the medium looks like when there's nothing in it, when there's no energy being transmitted. With transverse waves, we use, instead of compression and rarefaction, we have different terms, because no part of a transverse wave is squeezed together and no part is stretched apart. A crest is considered to be where the medium is at its maximum displacement, and the trough is considered to be a point where it's at its minimum displacement. And this goes back to the idea that, as I said before, can you have transverse waves that are, the medium is vibrating left and right and the energy is traveling towards the sky? Yes, you can, but we almost always draw them this way. So if I were to freeze this, I want to go to a higher frequency. If I were to freeze this at any point in time, there's always going to be a place on the wave that is as far above the equilibrium position as there is a part of the wave that's as far below. And the maximum displacement occurs right here, and that's why this would be called a crest. This would be called a trough. They're both maximum displacements. It's just that one is above and one is below. And this is why I'm making a big deal about saying to you, this is how we normally draw these things. Because if I was going to capture it, but I got to move a tool over so I won't bother. Because if I say to you that we have this transverse wave, it's meaningless to talk about a crest and a trough. A trough is like, well, it's a trough. A trough is an English word that means something that would hold water, maybe. And the water would take on that shape that we have at the bottom of this wave. A crest, when you crest a hill, you're going over the top of the hill. So trough and crest don't really have any meaning when it comes to a wave like this. So again, that's why we like to talk about waves that are transverse. And that's a horrible looking wave, right? But you get my drift, I think. So crest is where the medium is at its maximum displacement above the equilibrium position. Trough is when it's at the maximum below. Wavelength is the distance from one crest to the next crest, or from one trough to the next trough. Again, assuming that it's a uniform wave. So again, I've captured something, and we want to label crests. Well, this would be a crest. I'm just going to put C for crest. This would be a crest. This would be a trough. T for trough. This would be a trough. By the way, I don't know that you would, but sometimes students do. Don't try to equate a crest of this kind of wave with, say, a compression of the other. Crests and troughs are as different to compressions and rarefactions as flavor is to color. I mean, there might be some connection. They both have something to do with waves. Flavor and color both might have something to do with food, but they're different things. The wavelength would be the distance from trough to trough, or from crest to crest. Now we have to talk about period, frequency, and wavelength in more detail. Wavelength in more detail, period and frequency. We're going to adapt what we've learned about period and frequency for things like circular motion, for things like spring oscillations or pendula, to waves. A wave consists of a bunch of simple harmonic oscillators. They're all dancing to the same beat, but as I said before, slightly out of tune, out of step with each other. Okay? It's like that, there's some song, row, row, row your boat. And then the person comes in after the second verse. We'll try it, because some of you don't know what I'm talking about. So I'll be first, you be second, You be third. Row, row, row your boat. That's where you start.
Row, row your boat.
Gently down. And everybody, we won't bother then. It's not going to work out. I would need to have a music teacher in here to coordinate everybody. How many of you know what I'm talking about? I think Frere Jacques has done that way too. Now I've really lost you. Okay, never mind. Never mind. Oh, through the magic of video editing, that won't even be in the video. The period of a wave is the time it takes the entire wave to go through one complete cycle. So I want to see if you can wrap your head around this. If I take a look at, and I will go a low frequency. So I want you to try to imagine that the period is the time it takes, we'll go with this middle dot, for this middle dot to go from the top to the bottom and back. Okay? I just want you to understand that's what the period is. How many of you can appreciate, though, that the length of time it takes that to go up and down is the length of time it takes the crest to go from here to here? It's the length of time it takes the wave to complete one wavelength. And this is really a better definition of period. So it's how long in seconds it takes one portion of the wave to oscillate once, but that's the same as saying it's the time it takes the entire wave to go through one complete cycle. So if you were standing, and well, we can go back to this. If you were standing here and you started your stopwatch now and you ended your stopwatch now, you're going to get the period because that's going up and down once. But you will notice as well that that trough or crest has moved the wavelength in that period of time. It's a difficult thing to wrap your head around. The frequency of the wave is the number of times the material oscillates in 1 second. It's how many complete oscillations per second the medium makes. So estimate 1/1000. It's going through a complete cycle about every 1.5 seconds. That would be the period. The frequency would be one oscillation divided by 1.5 seconds. In other words, it's the reciprocal of the period. What I'm getting at is nothing has really changed here. We're just looking at the bigger picture of a wave. The frequency is still how many oscillations per second. The period is still the length of time it takes to happen. What determines the frequency of a wave? So I want you to imagine that it's a perfect world, and we'll stick with this type of wave, and somebody is holding a spring on one end and they're shaking it up and down. And it's perfect. There's no friction, there's none of that stuff that's messing up the wave. What is going to determine the frequency of the wave? Christina?
The speed of how fast you move?
We're not going to use the word speed. I'm going to even simplify your response a little bit more. The person does. And we don't want to say speed. I know what you mean, but it's really the frequency. So if I am sitting, so we'll answer the question first, and then I'll give you an analogy. What determines the frequency of the mechanical wave? It's the frequency of the source. And everything we talk about here in terms of my analogies is not perfect, but I hope you get the idea. Summertime comes, I go out to the lake, I'm sitting on the pier, I've got my music going in my ear, and my feet are just barely touching the water. And I'm listening to Wish You Were Here by Pink Floyd. And many of the songs on that album are very mellow and laid back and very slow beat. And I'm swinging my feet to that beat, the slow, slow beat. I don't know if you can see my feet, but they're just moving. And every time my foot hits the water, it pushes the water down, and then when my foot comes out, the water comes back up. So I'm going to get waves traveling away from me. And because I'm pushing the water down and allowing it to relax, say at 1 hertz, 1 frequency per second, that water that I've made contact with is in direct contact with the water further out, and it will also, because it's physically connected, it will also be moving up and down at 1 frequency, 1 hertz rather. And it doesn't matter what happens over here, whether the water gets really muddy and thick, or whether it's occupied by a bunch of fish, because everything is physically connected back to that initial vibration, everything over here is still going to go up and down 1 time per second, right? And then I get a little bored, and I switch gears, so I listen to my favorite Viking thrash metal album, and my toe is going in and out of the water like that, right? I'm going to be forcing the water up and down very frequently. And again, that water, and this is important for in a minute for something else, that water is physically connected to the water surrounding it. So all of the water, by way of physical connection, ends up having a very high frequency, maybe 10 hertz or 5 hertz, depending on the song. You get my drift? So it's about the source. What determines the speed? What determines how fast a wave travels through a medium? And I'll tell you right now that whether I'm listening to Wish You Were Here by Pink Floyd or whatever album by my Viking thrash metal favorite band is, the wave will travel at the same speed through the water, regardless of the frequency. And this is where it becomes difficult not to confuse speed with frequency. Because frequency has to do with, I'm going to stick with a water wave, frequency has to do with the material moving up and down, whereas speed is how quickly the energy can transfer from one place to the next. Any idea? Almost nobody ever gets this. It's the medium. It's the medium. It's what's doing the oscillation. If the medium is very flexible, then that's going to determine the speed at which the energy goes through. If the medium is very rigid, that's going to determine the speed with which it goes through. So it's, I don't want to say that, well, I will say the density and properties of the medium. So if I take a tub of water and I dip my finger, I tap the top of the water, you will get a wave going through it, and I'm sure you can kind of imagine how fast it will move. We would always, at Christmas as kids, have, I called it shaky pig. It's called studenettes. Do you know what studenettes are? It's a Ukrainian dish. It's head cheese. It may be pronounced differently with true Ukrainian. It's pork and ham in a gelatin.
Oh, holodets.
What do you pronounce it as?
Holodets.
Okay.
Yeah.
Oh, thank you. We call it studenettes. Now, I don't know where that pronunciation or English translation comes from, but it's shaky pig. That's what we called it. None of us kids liked it, and it turns out it's really delicious. It's good. It's got very good flavors, and we would always poke fun at everybody eating it because you could tap it and you could see it, or some people would call it jiggly pig, because when you tap it, it would all jiggle. But when you tap that stuff, the other end jiggles almost instantaneously because it has a very, very high density. Okay? So it's the density or properties of the medium. Now, the wavelength is the distance the wave travels during one complete oscillation. Before we do this question, I want to throw something your way. The speed of a water wave is the same regardless of the song I'm listening to. Okay? So imagine me tapping my toe in and out of the water at about 1 hertz per second, or 1 frequency. not frequency, 1 hertz, 1 oscillation per second. What happens is I create a wave front or a wave crest, and in the time it takes me to create another one, that first wave travels out at a certain speed, right? And when I tap the water again, the distance it will have traveled is the wavelength. That will be how far apart the crests are. I want you to answer this question. What will the crest distance be? What will the wavelength be if I tap my toe in and out of the water more regularly, more quickly, more frequently, I guess is the best word? Will the crests be further apart or closer together? Closer together. So the reason for that is, with the 1 hertz, when I tap my toe in and out of the water 1 time per second, the wave has the opportunity to travel however far it can travel in 1 second, and that's going to determine the wavelength. But when I'm doing it 10 times per second, that wave only gets a chance to move out a little bit. And that means the next crest is going to be very close to the first crest. So what happens is the frequency goes up, the wavelength goes down. Okay? So what are we asked to do here? Use the idea that the wavelength is the distance divided by, shouldn't say divided, the distance divided by, I'm still going divided, is the distance traveled in 1 oscillation. Okay. What do you call the time for 1 oscillation? What is that called? Sorry?
Period.
It's the period. So this is the period. What do we call the distance in 1 oscillation? What do we call the distance the wave travels in 1 oscillation?
Is it the wavelength?
Yes, sir. It is the wavelength. So this is the wavelength. So how can we find the speed of a wave? Well, speed is distance over time. And that's the wavelength over the period. But we don't like to talk about the period of a wave. I mean, we can, but when we talk about a wave, like a light wave or a water wave or a radar wave or a sound wave, we talk about frequency. You're familiar with the idea that there are frequencies of sound, and we can't hear all frequencies. Okay? Well, we want to change this equation, and since period is the reciprocal of frequency, I can write the speed as the wavelength over the reciprocal of the frequency. Fair enough? Okay. But whether you multiply by the reciprocal or use some kind of math trick that I've taught you in Math 20, that means that the product of frequency times wavelength is equal to the speed. And this is really interesting because the speed is determined by the medium. So if I have water waves, the speed of the water wave is the same no matter what. So if I increase the frequency, the wavelength has to get smaller, which is what we just explained. If the water is oscillating very quickly, the ripples are very close together. We can talk about longitudinal, but it's difficult for me to describe to you. If this moves back and forth very infrequently, we'll let it settle down again, you will see that those two compressions are quite far apart. Right? From there to there. Okay? But if I do it like that, they're very close together. So the higher the frequency, the shorter the wavelength. The lower the frequency, the longer the wavelength. And we're just going to do a couple of calculations now. This is called the universal wave equation, by the way, because it works for transverse waves, it works for longitudinal waves, it works for waves whether they're mechanical or electromagnetic. So this is called the universal wave equation. And on your formula sheet, it's under waves, where you see V equals F lambda. That's the formula we're talking about. Let's do the examples. A sound wave travels at 300 meters per second, and it has a wavelength of 2.5 meters. This is hard to visualize. It's easier for you and me to visualize ripples and crests and troughs. What it means is if I'm standing outside speaking to somebody on the other side of a football field, I'm going to be creating compressions in the air, and the distance between the compressions will be 2.5 meters apart. There'll be, here's a compression, here's a compression. And those compressions are going to be traveling through the air because, of course, it compresses the next piece of air, which expands, and you get that domino effect. And those things move at 300 meters per second. It's not something we could see, even if we could see the pieces of air. 300 meters per second, what's 300 meters per second in kilometers per hour? No, you know what? We don't even need to do that. A football field is about 100 meters. Yeah? 300 meters per second is 3 football field lengths in 1 second. It's fast. Okay? What's the frequency and period of the sound wave? So we know the speed is 300. The wavelength is 2.5 meters. The universal wave equation says if we take the speed divided by the wavelength, we're going to get the frequency, and then we can calculate the period by taking the reciprocal of that. I want to say 120. Yeah. So the frequency is 120 hertz. So now try to wrap your head around this. These compressions of the air are 2.5 meters away from each other, and they're all moving at 300 meters per second through the air. When I say the compression is moving through the air isn't moving that fast. The energy is moving that fast. But to boot, every piece of air is always moving back and forth 120 times per second, which is an amazingly high frequency for something like this. What's the period? The period is the reciprocal of the frequency. So it's 1 over 120 hertz. And again, we will get a number here that allows us to, kind of wonder about this. Like, that means each molecule in the air, whether it's an oxygen molecule, an errant water molecule because it's misty out, whatever, they're going back and forth one complete time every 8/1000ths of a second. So 0.08 seconds. We were also asked how long does it take the wave to travel 1 kilometer. There's nothing wrong with simply using speed equals distance over time, right? The wave is traveling at 300 meters per second. We want to know how long it takes to travel a kilometer, which is 1,000 meters. I feel as though I shouldn't even need to do that calculation, but you can put 300 meters per second in for V, 1,000 meters for D, and I'm getting 3.33 seconds. Yeah? Okay. So T is equal to about 3.3 seconds. By far, the vast majority of this lesson is about all of these terms and types of waves and you visualizing what they mean. But you do have a few questions relating to the universal wave equation and working with frequency and wavelength and distance in general for waves. By the way, remember that those air molecules are going back and forth 120 times per second. You can hear that. You cannot hear air molecules moving back and forth 10 times per second. I shouldn't say that. 1 time per second, you can't. You know why? Because your eardrum just physically is incapable of going back and forth 1 time per second. That air hits your ear, and your eardrum doesn't move because of it. I'll check on the range of human hearing one, you still might be able to hear 1 hertz. I don't know.